Okay, so this is going to be a completely unscripted but guided tour through the Starduster II high altitude balloon project. This is going to be for the Kickstarter backers, and I'm sure also make it available to others just to kind of step through the chronology of this particular launch. If you're interested, we're going to have updated photos, videos, links to data collected at the starduster.info website that I maintain. And you're always welcome to email me at josh_ward@me.com for questions about this project or any launches that you might want to conduct. I can offer you a few how-tos, some best practices, and give you some insight as to why we decided to do what we did as we went along. This is my second high altitude balloon launch. Um, First one was independent, just myself, my girlfriend, now wife at the time, Liz, a number of Kickstarter backers, and a handful of folks here in the area that assisted on launch day. A few guys from the Baylor Amateur Radio Club contacted me earlier this summer and said that they were interested in doing a launch of their own. They were interested in some of the radio experimental payload aspects, hanging a repeater from 90 to 100,000 feet. They were also interested in doing a lot of data collection using Arduinos, which I was very excited to help participate and help with the launch. So one of the first questions I always get is, why is your project called Starduster? And the answer is, I also happen to be a pilot, and the very first aircraft I ever flew was a Stolp Starduster II, specifically this one, tail number November 21 Echo Juliet. Um, I have a good friend who owned the airplane and passed away, and another good friend in California who bought the airplane where the airplane resides now. And at the point where I needed to create a project on Kickstarter, Kickstarter requires you to name a project, and I just had Starduster on the brain. So that is why these two launches have been Starduster 2, or still Starduster 1 and Starduster 2. A lot of high altitude balloon guys, teams will pick a name and then just increment their name by one. So I have a feeling there will be a Starduster 3, Starduster 4 type launch. But as to why I named the project Starduster and not High Altitude Balloon Project or whatever, just it was this particular airplane, which is a Stolp Starduster 2, fully aerobatic, open cockpit biplane. And so that's why. We were Kickstarter funded. For those of you who are interested in Kickstarter funding, I've got some ideas and some theories on maybe how best to accomplish it. I have attempted to fund two projects, and I have fully funded two projects. You can see that we were looking for $1,000 goal. We actually met our goal within the first 4 or 5 days of the project. We had a number of backers that had committed before we started funding. So we had already reached about 60% of our goal within the first 3 days. We had a backer or two increase their pledge or their backing because they wanted us to actually know that the project would make. And then the project didn't go stale. We just didn't push for much backing over $1,000 until sort of the last 72 hours. And then we had another backer or three come in. And so we were funded at $1,800. We got 187% of our funding. 50 people ranging anywhere from $250, $300 a piece. The average donation, as you can see, was right at $38. We got together, and this was sort of the initial drawing. I would say the back of the napkin, but this was actually a dry erase board. We knew that we weren't going to be able to fly a 1,200 gram balloon. We knew that we were going to have more weight than that, so we knew that we needed to settle on a 1,500 gram balloon. We originally had thought that we were going to build 3 payloads. Come to find out, due to weight restrictions, we were able to take the repeater, the radios from one payload, combine them with the camera payload, and eliminate one whole container. And then for the sake of the camera's movement, it was going to be better if we actually put the cameras in the middle and dropped all of the sensor data down to the bottom. So the final iteration actually only has two payload containers, but from top to bottom would have been the balloon. Beneath that would have been the parachute, which is not reflected in this drawing. And then the cameras with some of the antennas coming out of that payload container, and then beneath it was Jacob's all of his sensor data, which I've got some more photos kind of explaining how that goes. And then after that, we got a mission patch, because no program is official until you have a patch. I'm very, very flattered, very excited to show this patch. We actually are having a number of them printed, embroidered, and so I'll be sporting one of these, I'm sure, on a hat or a jacket or sometime soon. But we have an emission patch, so you know we're legitimate. We flew 4 cameras. Just so happens that this is a GoPro Hero 3. We had identical 3 Plus. These are the 2 that flew on my original flight. And then we had an upgraded 4K camera. This was the backup GPS tracking device. This is what originally flew on the original Starduster flight. And this was my first kind of mocking up for space in the payload. This is an Arduino with just a very basic, this is an ultrasonic sensor and then some batteries. Eventually, what got built was maybe 3 times as tall, but basically the same footprint. As I began building the payload container out of spare scrap styrofoam, I needed to mock all this stuff up so that I could kind of build around and get my measurements right. We did some pretty extensive testing on GoPro battery life. All batteries have serious performance degradation at cold temperatures, and we knew that we were going to be potentially down to minus 30, minus 40 degrees. And so we needed to know how long the batteries would last. And so we did some testing with the GoPros at room temperature, and we got a baseline of about 4 hours and 20 minutes on the different makes and models of cameras, and then with the extended life batteries. And then we put the cameras into my freezer and ran a few tests a few nights in a row, and we're able to consistently get battery lives of about 3 hours 15 to 3 hours and 30 minutes, which is what dictated our mission time. We needed to be up and down in about 3 hours and 3 hours 15 minutes to be safe, to be able to capture video. The other data collection and the other tracking, we were getting anywhere from 8.5 to 11 hours of tracking information. So tracking the payload down was not going to be an issue, but if we wanted video the entire way up and the entire way down, we knew that we needed to be up and down in about 3 hours. So that was all dictated by the amount of time the cameras would stay alive in cold temperatures. So this is my freezer. I wanted to do some testing on the GoPro cameras using stereoscopic vision, with your eyeballs having a left and a right eye. The fact that in the near field and the far field you get depth perception. We were interested in testing and putting 2 cameras side by side shooting identical angles, and we wanted to do some testing to see if we could actually get some 3-dimensional video, or the ability for your eyes to perceive being at 100,000 feet. Knowing full well that at 100,000 feet there would be nothing in the foreground to give you a sense of that depth. Perhaps at the balloon's burst with little bits of latex sort of floating around in front of you, and perhaps as we were going through some clouds and rushing down at the ground. So I wanted to do some testing in that, and it was successful. At this point, we haven't actually rendered all of that video and rendered the left eye and right eye video for like an Oculus Rift, or there's other cameras, there's other ways to use this video. and we have not actually processed all that. This video is about 10 days post mission, and we are still processing photos and video and all of the data. But I wanted to get this update out for the majority of the Kickstarter backers and some other friends and family that are interested in this project. So what we have in front of us is what I'm calling a hot iron. It's basically an ice pick that gets incredibly hot. You plug it into the wall. It's got an on-off switch, and what that allows me to do is carve out, very cleanly carve out styrofoam. And so I make my payload containers from scratch. I build them so that the cameras mate and kind of mesh directly into the wall and leave a very minimal amount, just the lens exposed to the outside world. Keeps the payloads a little bit cooler, a little bit cleaner. I like to think that they're a little bit more elegant. And I can't do that inside of a store-bought, like a beer cooler or a styrofoam container. So I find it easier just to take a sheet of styrofoam, cut it into the size walls that I want, and then carve out the camera face. Uh, I would say it's a very scientific technique, but basically all I do is mash the camera into the styrofoam, and wherever it makes contact, cut out a little bit of a hole, and then remash it and figure out where it makes contact and cut out a little bit more of a hole. And what you see here is multiple attempts at that. So this is us testing the stereoscopic cameras. Sort of a look at some basic wooden joinery. It's just some wooden dowels that I use to help reinforce the construction. This is without the cameras in it. This is hanging in my home office. I wanted something that would allow the cameras to swing around to offer, again, a sense of depth. This is a still frame from inside my garage. You can actually see that the left eye and the right eye are seeing slightly different things, which is what you want because your left eye and your right eye see things slightly different. And then when your brain mashes them together, it offers you a sense of depth. So with the right viewer, you could go to this GoPro stereo test that I put together, and you can actually get a sense of depth as this payload is swinging around inside of my garage. It's slightly nauseating, but it was definitely a good test, proof of concept. So we began to build the actual walls of the container. The way this is arranged is this is the two 3 pluses, the GoPro 3 pluses. The GoPro 3 went into this side, and then the 4K camera went into this side. So this is sort of the fore and aft windows of my payload. Eventually building them into a box where it would accommodate, again, 2 out the front, 2 out the back, constantly monitoring weight. We definitely had weight restrictions due to the performance envelope of the balloon. I took, and all of these seams are glued with just pretty standard Elmer's glue, but then to reinforce the construction, taking that hot ice pick, was able to melt deeper into the styrofoam, pull it out, and then drag a wooden dowel and press a wooden dowel about 1.5 inches into the walls. So it's just basic joinery, but it allows the construction a little bit more strength, allows some torque, some twisting, allows some flexibility, but also some strength in my payload containers. So this is next view is a top-down view. This is sort of a clean look at how my payload container looked without any of the wires connecting. You can see again the cameras. These are the two 1080 resolution cameras. This was the 4K camera, and this was the camera that was dedicated to taking 10 megapixel still photos. We flew a repeater configuration in the amateur radio frequencies. This was our uplink radio, which was tied together to the downlink radio. I've got a slide here in a second that kind of explains that process a little bit better. But both the uplink and the downlink radios flew in my container. This is a look at sort of that configuration. The uplink antenna actually was outside of the payload container on some of the strings, on some of the strands that held the payload train together. On one frequency, this radio would detect that somebody had keyed the mic and would bring the voice communication through this path, through an isolator to this box that I jokingly call the flux capacitor. Basically, the headphone jack of this radio, the moment this box detected that someone had keyed the radio, it then keyed this radio and opened up the channel and allowed anybody talking on this frequency to be heard and rebroadcast back down on this frequency. And because of our vantage point, some 90 plus thousand feet above the Earth, we were able to pass radio traffic that normally would have had a 2 to 4 mile type range. In theory, we were going to realize up to a 450-mile range, depending on the wattage of the communications coming in and going down. One of the interesting things about having a repeater that is unmanned at 90 plus 100,000 feet is the repeater, according to the FCC and amateur radio rules, has to identify itself periodically. So one of the things Jacob did was built an Arduino device that in once every 8 minutes would I call it inject, would send Morse code down that same pathway and ID the repeater. So to keep the FCC, amateur radio guys, everybody happy, anybody that knew the right frequency to talk up could be heard, and then periodically to keep legal, the repeater has to identify itself. So we had a device built, or Jacob built a device that would encode the Morse code ID of our repeater and broadcast that back down on that downlink radio. So this is what my payload looked like adding all of the radio components. There are still one or two little pieces missing that you don't see here. I did carry a 9-axis motion sensor because I wanted to be able to take motion data, which we're still trying to figure out what all we can do with that data. But I have some 75 megs worth of motion data that we can marry to the video. This is just a quick look at what the Starduster II payload looks like compared to the original Starduster I payload. This is actually, I believe, after we recovered the payload. You can see that there's no dents, no scratches, no dings. It's actually in very, very good shape. This is the original Starduster payload. You can see where it came down and sort of crunched in one side. But just to compare the two, this one probably has about 40% more volume. We're carrying 2 more cameras and 2 radios that I was not carrying in the original launch. This is a look at Jacob's build. Jacob's payload was able to take GPS data. There's a GPS receiver, and take that GPS data and split out. One bit of that GPS data was coming to some data logging, and then the other bit of GPS data was getting sent down to APRS through a third radio that we carried. So in total, we carried 3 radios, 2 for the repeater, uplink and downlink, and then we had another radio that was acting as a transmitter to transmit the payload's GPS, latitude, longitude, altitude, and maybe 1 or 2 other little bits of data. But in addition to transmitting that data, attempting to transmit that data once per minute, we were logging GPS data once per second, along with other sensors. This is 2 of the shields. One of the shields Jacob built by hand, and then the other shield. So the bottom is the actual Arduino. This is the SD card shield. This is just basically what allows the Arduino to take inputs from multiple sources, 2 temperature probes, barometric pressure, humidity, some other points of data. All of that data is able to take and get encoded by this guy and written to an SD card for us to examine and process later, which I can show you some of that data, how that data looks. But Jacob did a phenomenal job building this shield from scratch, and then using some off-the-shelf Arduino shields for the rest. This is the inside of Jacob's payload, a little bit cleaner. He's not having to carry as much of the radio gear and the camera gear as I did, but this is that same Arduino with multiple shields. The barometers were quite tiny. We did have humidity. There was an internal thermal, an internal temperature probe, and an external temperature probe. We wanted to get the delta, the difference between the internal temperature and the external temperature. And then some of this is the GPS sensing, encoding, and transmission type equipment. So this was the sensor payload. That's a look at Jacob's. Jacob didn't carry any cameras, so he didn't have to have any windows. His dimensions are nearly identical to mine. So both of the payloads that flew were nearly identical. I believe his was in the about 2.25 pounds. Mine wound up being a lot closer to 4.25 pounds for a total payload somewhere between 6.25 and 6.5 pounds worth of payload. So knowing that information, this is not our final payload mass, but this was some of our initial calculations. The initial payload calculations were about 3,600 grams, 454 grams per pound, etc. This is Kmont's prediction, or somebody's prediction, of a Kmont 1,500 gram balloon. Plug a bunch of numbers in, find out what your ascent rate, your estimated ascent rate is going to be, time to climb. Knowing how long it's going to take your balloon to climb will tell you how long you're going to be exposed to wind, so that you can begin to build your model and build your map across the ground. So this is one of the tools that we use for estimating the route, building the route. This is a visual. This was our initial estimated balloon track. There's a video on my website where I explained why we picked Comanche, but to show you this model, Comanche, the balloon was climbing, 1,000 to 3,000 feet, nearly vertical, until it began blowing in a southeast track. We knew that we were going to be able to drive along these roads and track sort of underneath the balloon to Gatesville, eventually to McGregor, and then cut down to 7, and we were going to try to recover in the Cossie area. Maximum height we had actually estimated was going to be 92 to 93,000 feet because we were so heavy. Come to find out, we actually realized more altitude. We actually got up to 99,155 feet. So the reason that we picked Comanche just had to do with the fact that we had a wide open area there at the airport. We had access to the line shack, plenty of parking. We did contact, absolutely, we contacted the county sheriff, who had no problems. The city gave us positive feedback, and the airport manager welcomed us there to the facility, which is why we chose to launch from the Comanche Airport. Generally, I would avoid launching anywhere near an airport, but upon contacting the FAA, filing a NOTAM, we dotted I's and crossed T's. It just so happened that that particular day that was the right answer for us. Now, what we have is the notice that we issued to the amateur radio community, to the FAA, and all of our friends and family that we wanted to track, our progress. So this was a note that we had issued to a lot of the amateur radio guys. We had given multiple tracking options through APRS, through my GPS tracking device. We told everybody how to contact the balloon on the uplink and the downlink. We actually were multiple vehicles in the chase were also transmitting APRS data so that people could see where we were on the ground as opposed to the balloon's location. And this was the NOTAM that was issued by the FAA after contacting the FSDO. And this is not a great map, but this is the actual sectional that we use to sort of explain where the balloon was launching and where air traffic needed to be aware of an unmanned free balloon up to 105,000 feet at a date and time launch through a date and time estimated burst and landing. So this is the actual NOTAM that was issued. Again, it's an airspace free balloon off the Brownwood 077 radial, 18 DME, etc. This is what we had to issue to get the FAA in a loop, and they appreciated that consideration. And I will always recommend, whether or not it is required based on applicability, I would always recommend doing. So the morning of the launch, clearly I'm much more excited than Liz. Jacob and I are ready to get this thing underway. We knew that we would have 8 to 9 people assisting with the launch before the whole morning was over. We probably had 20 or 25 people on the ramp assisting with inflation of the balloon and launch. This is Jacob and Donnie helping me get my payload ready. We had cameras plugged in till the very, very last moment. Charging, radios charging, we wanted everything topped off. But once we turned the cameras and the radios on, we knew that we had we had a finite amount of time. So we wanted to get everything ready. Once we got final weights checked, verified that everything was the way we wanted it to be, we went out and measured how much free lift we wanted in the balloon. Again, we were lifting approximately 3,600 grams. We knew that we needed about 850 grams of free lift. So whatever that number is, 4,400, 4,500 grams is what we needed the water bottles to weigh. Once we knew that we had water bottles weighed that were the payload plus the free lift, we could begin inflating the balloon. This is me actually getting the neck of the balloon attached to the custom hose that we built. That's a 2,000 psi helium bottle regulated down to about 5 or 6 psi. And then I've got a little quarter turn valve where I can actually shut the flow off to the balloon as needed. In fact, there's the rig there. Again, 2,000 psi bottle regulated down to 5 to 6 psi. And then I've got a shut off where I can turn that on and off. The balloon neck receives this head very, very well. It allows us, it's got a pretty good grip, but we keep a good grip on it. But it allows us to begin inflating, and then once the balloon turns upright, then we can begin hanging weight off of that and to try to neutralize the lift. So this is beginning the balloon inflation. This is probably a third of the way inflated. Again, we had a lot of good help on the ground. That morning we had probably 12 to 15 people assist at some point in the actual inflation process. We thank all of them very, very much. Now the balloon has actually gone vertical, and we're beginning to hook up the weight onto the balloon, onto the neck of the balloon, to begin sort of gauging how much lift the balloon is getting. At the point where the balloon is able to pick up and sort of neutralize that heavy, heavy weight, then we can begin assembling and adding the parachute and all of the other payloads. And it's at this point that the balloon has enough lift to carry the water bottles. So then we'll begin to snap on the parachute, and then my payload, and then beneath my payload, Jacob's payload, and then when we remove the weight, we'll be ready to launch. So this is just, again, part of that process, getting my payload strung underneath the parachute. This is my payload with an if found. You can see the antennas coming out. This is the downlink and the uplink antennas, and then the face of 2 of the cameras with the other 2 cameras facing out the opposite direction. Pat assisting Jacob closing up his payload. They've just begun data collection. If you ever get a hold of our data, which we'll release, there's probably 5 minutes of just data where the balloon is sitting on the ground waiting to go. That's during this process while we're getting all this buttoned up and ready to launch. This is actually what the payload train looks like at launch. 6-foot diameter balloon at launch. Eventually, this size balloon will grow to 32-foot diameter. So it goes from 6-foot diameter at launch all the way out to 32 feet diameter at burst. At the point where it bursts, the parachute is able to expand out and become effective at slowing the payload down. You see my payload and you see Jacob's payload beneath me. That decision was made because my cameras would be swinging around wildly, but with Jacob's payload beneath mine, mine's not able to swing on that pendulum because his actually dampens my camera's movement. So my cameras look much, much better. The output for my cameras look much, much better on this flight than the prior flight because of the weight of Jacob's payload beneath mine dampening any kind of oscillation and movement. This is the payload actually on the climb out. You can see that I have the uplink antenna, the downlink antenna, and then Jacob has a separate antenna for APRS. And that begins the balloon's 750 foot a minute ascent. For those of you who are not participating in the chase, we actually had about 8 vehicles, maybe 7 vehicles participate in the chase. It was probably 150 miles or so of driving east across Texas. We made 3 or 4 stops en route just so that everybody could stop, get a break. Called them bio breaks, but that allowed everybody a chance to double check their radios. We could make some calculations and figure out which roads we wanted to take. The balloon followed the path that we expected. We didn't expect it to get as much speed as it did, and at the point where the altitude went higher than we anticipated, we had to make some decisions late in the route on were we going to follow our original plan or did we make some modifications, which we did. So this is just kind of an example of what it looks like to chase a balloon. These guys came down from the Dallas area. They actually had a mobile rig that allowed us some communication with the balloon, potentially allowed us some communication with the balloon that you wouldn't normally have in a vehicle, even if you have lots of antennas. These guys enjoy chasing balloons. They enjoy radio experimentation. I mean, they are what ham radio is all about, and we enjoyed having them on the chase. Thank them very much for helping us locate the balloon, especially in the last half mile on the ground. So this is a look at what we were seeing. This is a few minutes after launch. In fact, this is about 50 minutes after launch. You can see our vehicles were being tracked along the road. This was the path that our vehicles were taking, whereas this green path is the path that the balloon was taking. Every single one of these dots is the balloon checking in. And so you can see as the balloon climbed out near vertical, nearly straight up, we got lots and lots of information from the balloon. But as the balloon got higher and higher, we actually got less and less information from the balloon, which is just a product of the way Jacob had the receiver and the transmitter set. The higher we got, the more exposed to other people's traffic, and our balloon couldn't get a word into the network. The one thing I do think that is very interesting is that this is the actual speed in kilometers per hour at the altitude. So basically at 36,000 feet, we're doing nearly 140-ish, 150 miles an hour. So while we got out ahead of the balloon because it was climbing straight up, eventually at some point it started moving across the ground very, very quickly and blew right past us. In fact, when we made the turn at Gatesville, it had passed over McGregor at 60,000 feet, and it slowed down at this point at roughly 40,000 feet, 40,000 feet. No, that math is not right. Doesn't matter. The balloon is slowed down considerably. It was in the jet stream from about Turnersville to around McGregor at 60,000 feet. We'll go into the speed across the ground data here in just a second. That graph is very telling. This is probably one of the last packets that we got at altitude. This is one of the highest reports that we got from the balloon. We were tracking data at once per second inside the balloon, but as far as its ability to report its position back to us, this is probably one of the highest packets that we were able to receive. And again, you can see the ground traffic on the ground was just getting beat into the dust by the balloon traveling across the ground at, what is that, like 70-ish miles an hour. The one thing that is also interesting is that another tracking group came down from the Dallas area. They left Hillsboro north of Waco about the time the balloon was launched, and they got out and stayed out ahead of the balloon's progress so that as the balloon was coming down after burst and as the balloon got near the ground, they were going to be able to get to the balloon and offer us some valuable information on where the balloon was coming down. This is the last packet that we received from the balloon at 2,800 feet above the ground. One of the things that is very interesting and very telling is the entire flight, it was on a 8-4, basically kind of a pure east heading, headed purely east very, very quickly, although this camera may be backwards, so maybe this is your east, I don't know. But the data, everything about the balloon was headed east. This is my east. Everything about the balloon was headed east until the very last packet, and that was 2,800 feet above the ground. And it actually slows a very slow turn back to the west, which is very important because whenever we got to this area, because there was so much east travel, if we had taken that point and we'd started to head east by a half mile or a mile, we never would have found the balloon. The fact that the balloon was able to report to us at the very last moment that it was in fact headed to the west very slowly, the search party on the ground started moving that heading. We kind of built a cone and said, if it came down to the west, we ought to look in this area. And it was within about a quarter mile of where this actually says it should have been. So it was very important to pay attention to the data because the balloon was not headed east in the last 2,800 feet. So this is a look from end to end. This is all of the points of data that the balloon sent. Again, climb out near vertical, got caught up in the jet stream, was going super fast to about this position, and then slowed down and continued to climb up to, this is the highest point that the balloon reported in, was 96,000 feet. Although we did get data that said we got higher than that, the actual payload data being sampled at once per second showed us an altitude of 99,155 feet, at which point the balloon burst and then came back down through the same wind profile, but came downhill much, much faster, eventually landing between, about halfway between Kasi and I-45. In this general vicinity. So this happens to be the highest packet that we got in the entire trip. What I think is very interesting is if you were to compare the actual track with the predicted track, you'll notice the shape of the predicted track and the actual track are nearly identical. The only real difference is the prediction had burst around Loop 340 in the Waco area, whereas the actual burst, because we flew higher, the actual burst was more southeast of town, which meant that instead of landing in the Kasi area, you'll notice that we actually landed about 12 to 14 miles east of the original prediction. So we went higher and we went longer than we originally thought. This is an actual drawing that shows across the ground the trip the balloon took in red. If you just measure the latitude and longitude point to point, roughly 140 miles travel exactly as the crow flies point to point. Probably more like 160 miles if you count all of the little turns and jigs that the balloon took till its final resting spot. From our vantage point at 99,000 feet, we were able to do some experiments with folks on the ground and their ability to talk through our repeater package, our repeater payload. On radios that should, because of the curvature of the Earth, only have about a 3.5 mile range, or perhaps a 7 mile range, we were able to, because of its vantage point, using this radio horizon calculation, we were able to calculate the distance of how much range an antenna that high is able to see due to the curvature of the Earth. And so, without getting into the deep, real geeky math, from approximately 100,000 feet, according to this equation, we could have, in theory, had about a 450-mile radio horizon range. This next map shows you that from 99,000 feet, this is sort of the theoretical range that anyone in this green circle could have seen the balloon at altitude and communicated down to somebody else in that range. So, I mean, in theory, somebody in Beaumont could have been communicating with somebody in Abilene, somebody in Ardmore could have been communicating to somebody, down in Victoria or Rockport on radios that honestly have about a 3 to 4 mile radius. So, for a brief time period, about an hour and a half, we were kind of a radio satellite. We weren't a satellite, we were just a repeater payload hanging from the bottom of the balloon. Uh, that's in theory. The radio actually ceased to function at about 60,000 feet on the ascent. Part of it had to do with some configuration issues that wore the battery out. The battery expired. But from 55 or so thousand feet at this location, our radio range, our radio horizon was more like this white circle. This was the effective range, what we got out of it. And in another video, which I've got published on YouTube, we actually have radio traffic of people in Cedar Park, Austin, and North San Antonio able to communicate with people in Allen. So we did not fully realize the theoretical range of the balloon, but in practice, we do have radio communication that we recorded and documented from northern San Antonio all the way to the Allen, Texas area. So effective use. Now, as far as recovery goes, we came down in a very wooded area. We went out of our way to go find property owners to get permission to be on the property. This particular area is much more treed and much more wooded, even than this picture shows. But this is the condition of the balloon whenever we got to it, and this is what it looked like whenever we spotted it. The payloads fell perfectly on either side of a large branch. And you can see this is what's left of the balloon. The balloon shredded itself at altitude. And so you have the balloon connected to the parachute, which was connected to my payload, and then my payload is connected to Jacob's payload. That's the condition of the payloads whenever we found them. And this is us kind of hacking our way out of the brush to get back to the vehicles to get back home that evening. My payload, like I said, has been up and down. The cameras have no concept, no clue that they've been up and down. They're in perfect shape. All of the radios inside are still intact. Everything works perfectly. Very proud, very happy to have found our payloads. And this is part of the recovery team. There's only one or two individuals not in this photo that were not part of the recovery team, and we thank them, Ben especially, who took the photo. What we got back was lots and lots of photos and lots of data. This is an example of the data stream that we got back. This is, for instance, GPS time. This is the number of satellites, latitude, longitude. This is going to be altitude. And then sensor data. This is going to be temperatures, barometric pressures, different X, Y, Z axes, movement, etc. I included this particular shot because this actually does show somewhere right about here. This is the point of the highest data packet. This is our 99,155 foot packet. This is the actual point where the balloon burst and then began heading back downhill. So if we take this comma delimited file and drop it into some graphing programs, we find some very interesting data. Irrespective of the speed across the ground and heading, this is the ascent and descent profile, which you can see from the time of launch all the way up to 99,000 feet. It's almost a perfect linear 750 feet a minute climb. As we're climbing, the barometric pressure begins to bleed off. And you can see we actually reach about half of the available oxygen somewhere between 28 and 30,000 feet. And then once we reach 40,000 feet, we're down to little to no air, to the point where we reach 0.0363 atmospheres of pressure, which means that we were actually above 99.97% of the Earth's atmosphere. At the point where the balloon burst, there is no air, so the parachute and the square inches of payload rushing through the lack of air begins to build up a lot of velocity, a lot of speed downhill, until we finally get into more and more effective air. As the air gets more dense, the payload gets more effective and the parachute gets more effective and begins to slow down. At the point where we reach the ground, at the point where we reach the trees, my calculations show that we were doing about 20.5 miles per hour. This is one of the most interesting graphs to me. Again, same ascent profile, 750 feet a minute, but what you will find is the internal temperature inside of the payload goes from 65 degrees, climbs just slightly at launch, drops down to about 40 degrees at about 50,000 feet. But above 50,000 feet, you'll see that the temperature inside the payload climbs back to nearly 70 degrees. Basically, the higher you go, you would think the colder it gets, which is the truth, except that inside the payload, because of the radios, because of the cameras, because of all the things that generate heat, um, because there is no convection in a near vacuum, there is no atmosphere to give the heat to. So inside the payload, we actually only got as low as 40, which climbed all the way back up to nearly 70 degrees. External temperature sensor outside of the payload actually goes from 55 degrees at launch, which was the ambient temperature outside. It dips down to minus 65 degrees. And then from about the same point, 50,000 feet, from 65 degrees, there's actually a gentle warming outside of the payload, which shows that we were actually flying through some of the uh, upper atmosphere, stratosphere, thermosphere, into kind of where the ozone layer, as you've heard of it, is, because the solar radiation hits the ozone, strips off some of the electrons, and actually begins to heat up some of the atmosphere. So you see a very gentle warming, and I've got a better graph that'll show that here in a second, up to the point where the balloon bursts, and then everything comes crashing back through those same very cold temperature profiles. This is the balloon's speed across the ground. Again, this does not take into account the heading. This is just the balloon's forward motion. You'll notice through the first 10, 20,000 feet, the balloon never really gets more than faster than about 40 miles an hour. So the balloon's taking off near vertical. And then about 28,000 feet, between 28,000 and 44,000 feet, the balloon goes from 40 miles an hour, hits the jet stream, and the balloon actually travels as fast as 175 miles an hour at about 44,000 feet. Above 44,000 feet, you'll notice that the balloon speed decreases very, very rapidly above 50,000 feet, all the way up to 70,000 feet, where again it's climbing almost purely vertical through the next 30,000 feet all the way up to burst. This is basically the same chart, just kind of turned on its side. All it does is just show that at 28,000 feet, the airspeed begins to kick up. At 175 miles an hour, we're doing about 44,000 feet. We're doing about 175 miles an hour. Just looking at the graph again, you can see that the jet stream exists at that altitude profile. Coming back downhill, the speed of the balloon picks up again in that nearly that same identical profile. So we went up through the jet stream and climbed, and on the way back down, we got moved back again through the jet stream. This is the temperature profile again, just turned slightly. At launch, through the first 10,000 feet, through the first 20, 30, 40,000 feet, there is a linear, near perfect 2.8, 2.9 degrees per 1,000 feet, which is pretty close to the 3-degree standard lapse rate. The balloon reaches 0 degrees Fahrenheit, begins cooling down all the way down to minus 65 degrees, And then above 55,000 feet, you start to see that gentle warming as it's climbing through that ozone layer. So this is sort of our final statistics. This is what we got out of the balloon. Maximum altitude 99,000 feet. We were above 99.97% of the atmosphere. Minimum temperature, I guess the maximum cold that we got was minus 63 degrees Fahrenheit, and we reached over 175 miles per hour at 44,000 feet. The ascent rate was 750 feet a minute. It took us 2 hours and 12 minutes to get to burst. When the balloon burst, it only took us 27 minutes and 36 seconds to get back to the ground, with a final landing speed of about 20.5 miles an hour. So you could throw the payload at the ground harder than it actually hit the ground. I'm going to cycle through a couple of photos just to kind of give you a representative idea of what the balloon saw. Again, this is climb out. This is, maybe 100 foot above the Comanche Airport. This is looking mostly north and northwest. The route of travel is this way, which again on this camera I'm not sure it's going to help. Maybe the route is this way whenever I see this final output. This is climbing through sort of a layer of mist, through some overcast. This is probably 75 to 80,000 feet. This photo was taken with the 10 megapixel GoPro still photo on 1 second increments. This is probably 95 to 96,000 feet. Again, from that perspective, we can see 350 to 400 miles away on the horizon. Can't make out a lot of detail, but again, that's 350 to 400 miles away, completely all the way around the balloon. This is the moment the balloon burst. The balloon is designed to fail at 32 feet diameter. Little bits of latex, about 92% of the volume, about 92% of the weight of the balloon came back down. So people that are worried about littering, very little of the latex was lost. But that's what you see here is little shreds of latex when the balloon let go. This is the maximum altitude, 99,000 feet. Again, this is clearly you can see the curvature of the Earth. This is probably 2 frames, 3 frames, the first 2 seconds of free fall. And for a brief split second, you can actually see Jacob's payload. My camera pitched forward real hard and was able to look down and see Jacob's payload beneath us. You can see on the descent, it wasn't really violent, but the descent managed to shake some of the antennas loose. If you watch the video, you can kind of see the antennas whip in front of the video camera periodically. This is the moment we hit the trees, and the balloon actually hung for about 45 minutes, maybe an hour longer before the batteries were finally exhausted. This is the very last frame that was taken on the still photos. And then the recovery team was on site about 25 minutes after this particular photo was taken. And that concludes the talk that I prepared on the Starduster II launch. If you have any questions, again, you can email me at josh_ward@me.com, and you can check out starduster.info, the website. I appreciate your time, and again, any feedback, let me know. Thanks.